So we're going to continue with section 4.4 and finish out equations by talking about logarithmic equations. So we already talked about exponential equations where we change to a logarithm. Logarithmic equations are equations that already have a log in them, and we're going to change them back to exponentials. Now, the one thing that is a little bit different about logarithmic equations that we didn't have to worry about with exponential equations is the fact that logarithmic functions can have restrictions on their domains. And any time that we're faced with solving equations whose function has restrictions on their domains, we have to remember to check our solutions. We need to make sure that whatever value of x we come up with does not violate the domain of that function. And remember, what you're looking for is that I cannot take the log of 0 and I cannot take the log of a negative number. So we have to make sure that our value of x doesn't make an argument 0 or negative. Okay, now with exponential equations, I showed you a little shortcut up front that you can use when you recognize it. There's a similar shortcut for logarithmic equations. Now the shortcut will only work if you are able to take the equation and get a single log with the same base on both sides of the equal sign. So in number 1 here, I already have that set. So notice that I have a single log base 3 of 7 on the left and a single log base 3 of x plus 2 on the right. So there are no other variables except for the one that's in the argument. There are no other constants except for the ones that are in the argument. So if I can get the log of something equaling to the log of something, the only way that this statement can be true is if the arguments are equivalent to each other. So that means that I can go ahead and set this argument equal to the other argument and solve for x that way. So if I solve for x, I'm going to get x is equal to 5. And now remember, I have to check that value, and you always want to check it back in the original equation. So that means that I'm wanting to make sure if I let x be 5 in the original argument, that it keeps that argument positive. And of course, 5 plus 2 is positive. So I do get to keep that as my solution. Okay, in number 2, I do not have a single log equaling a single log, because on the right-hand side, I have the sum of 2 logs. However, we learned in a previous section when we were talking about properties of logs how to add 2 logarithms together. So I can combine the logs on the right in order to get it set up as a single log equaling a single log. So I'm going to have the log of x minus 3 on the left, and on the right hand side I'm going to go ahead and add those 2 logarithms together. And remember, to do that, the property says you take the 2 arguments and multiply them together. So the new argument on the right is going to be 2x. So now I have a log equaling a log of the same base. The base is 10. So I can go ahead and set the arguments equal to each other. So the only way this is true is if x minus 3 equals 2x. So if I solve that and subtract x from both sides, I get x is equal to negative 3. And again, don't forget to check your solution. So if I replace negative 3 in for x in that first argument, I get negative 3 minus 3, which is a negative value. And I can't have that. So that means that solution gets thrown out. If any one argument in the original equation becomes negative or 0 with your x, then it has to get thrown out. And since this was the only solution that I had to work with, and I threw it out, that means that this equation has no solution. Okay, so what happens if I can't get a single log on both sides, or I just don't recognize to do that? Then here are the standard steps for solving a logarithmic equation. What I want to do is get all of the terms that contain the log on one side so that I can combine them together as a single log. And then we're going to rewrite it as an exponential equation and solve it from there. So notice here in number 3, I could not achieve that single log on both sides because you've got this 2 over here that's not part of an argument. So you've just got this extra term. So I could not use that shortcut. So we're going to follow these standard steps, which I already have the logs on one side. So now I want to combine those two logarithms. So to combine the two logs with addition, that means that I'm going to multiply these two arguments together. So remember to distribute that x to that second argument, which will give me a new argument of x squared plus 15x. Now, once you have it rewritten as a single logarithm, now you want to change it to an exponential. And the reason I'm changing it is because to solve for x, I need to get those x's out of that argument position. And rewriting it as an exponential will do that for me. Okay, so now you got to remember how we go from logs to exponents. So I always start with the base, then my power, my exponent, and that is always equal to the argument. So my base is 10. Since there's no subscript on the log, it's understood to be base 10. My power, or my exponent, is always what the log equals, so that's the 2. And that always gets set equal to the argument. And that's an equation I can solve. So now my x's are out of the argument position, so I can solve this quadratic equation. So to solve a quadratic, we get it set equal to 0. So I'm going to move that 10 squared to the other side, and that would be subtract 100. So there's my quadratic equation that I'm going to solve. And to solve it, I'm going to factor. So I've got x and x in the first term of my binomials, and I need two factors of 100 that differ by 15. So the numbers that would work, the factors that would work would be a plus 20 and a minus 5. Their product is negative 100, and if you add them together, you get positive 15 for the middle term. So my two solutions are x equal to negative 20 and x equal to 5. And now I have to remember, I have to check my solutions. So if I start with the negative 20, and remember you want to go back to the original equation before you combine the logarithms together. And you want to look to see if it would make either of those arguments negative. And of course, plugging in a negative 20 to that first argument gives me an argument that's negative, so that value is gone. Don't always assume you throw out negative numbers in your answer, though. Sometimes you do get to keep some negative answers depending on how the argument was written. Now if I check my 5, if I plug 5 into the first argument, that would be positive. If I plug 5 into the second argument, 5 plus 15 would be positive. So I do get to keep that solution. Okay, let's move to number 4. Look, it's very similar to number 3. So this would be a good time for you to pause and try this one yourself, and then come back and see how you did. Okay, so we're going to add these logarithms together first. And my base is 6, so I've got log base 6. And since it's addition, I want to multiply those two arguments together. So if you need to go off and do a little bit of scratch work on the side and FOIL out the x plus 3 and the x plus 4, that's fine. My new argument then would be x squared plus 7x plus 12. and that all equals 1. And now I'm ready to write it as an exponential. So my base is 6, my power is 1, and I set that equal to the argument. So there's the equation that I want to solve. So again, it's quadratic, so I want it set equal to 0. So if I move that 6 by subtracting it, I'm going to have x squared plus 7x plus 6 equals 0, which will factor into x plus 6, x plus 1, giving me two solutions, x equal to -6 and x equal to -1. So now I need to check these back in the logarithmic equation to see if I need to eliminate any of them. So if I check first with the -6, of course, -6 plus 3 would be negative, so it's gone. As soon as I hit a negative or 0 argument, I throw it out. And if I check -1, -1 plus 3 is still positive. -1 plus 4 is still positive. So that one checks. So I do get to keep that as a solution. And again, just remember that you go back to the original equation before you combine the logs. Okay, so both of those, I combine my logs by adding the logs together. So let's look at two examples where I am combining the logs using subtraction. So I've got the difference of two logs equaling a constant, so I can't use the shortcut because of that 1, but I can combine these logarithms together. So I'm going to have log base 10. And remember that the property for subtraction says that you take the first argument and you divide by the second argument for your new combined argument. So I'm going to have the log of x plus 12 over x plus 2 equals 1. And once you've combined your logs, now you want to write it as an exponential. So my base is 10, my power is 1, and I set that equal to the argument x plus 12 over x plus 2. So this time I have a rational equation to solve. So to solve a rational, we clear out the denominator. So I'm going to multiply both sides by x plus 2, which on the right is going to give me 10x plus 20. And on the left-hand side, right-hand side, the x plus 2's will divide out and leave me an x plus 12. So to solve that linear equation, I want the x's on one side, the constants on the other. So I'm going to get 9x equals -8, giving me a solution of x equal to -8/9. And again, I need to check that solution before I keep it. And -8/9 is a little less than -1. So something less than -1 plus 12 would still be positive. Something less than -1 plus 2 would still be positive. Therefore, I do get to keep that solution. Okay, another good time for you to pause. Another subtraction problem. So take a second and try it yourself. Come back and see how you did. So to subtract these two natural logs, we're going to do the same thing we did in number 5. And our new argument is going to be the first argument over the second argument. So I've got the natural log of x plus 1 over 4x equals 0. And now we write it as an exponential. So I start with my base, and because this is ln, my base is e, my power is 0, and I set that equal to the argument. And again, it's rational, so I'm going to clear out the denominator of 4x. And on the left-hand side, of course, e to the 0, anything to the 0 power is just 1. So on the left-hand side, I've got 4x times 1 is just 4x. On the right, the 4x's divide out, and so I get x plus 1. Subtract that x, divide out the 3, and I have a solution x equal to 1/3 that I need to check. And if I go to the original problem, x plus 1, if x is 1/3, that's still going to be positive, and 4 times 1/3 will be positive, so I get to keep that solution. Okay, 2 more examples. This time I've thrown in a few extra constants just to make sure that we know how to deal with them if they show up. So in the first one, we've got 3 times the log base 2 of x minus 1 plus log base 2 of 4 equals 5. So I can't go ahead and add those logs together yet because of that coefficient of 3 out in front of that logarithm. But remember, we have a way to deal with coefficients. So we had a property that allows us to pull coefficients of logs in as exponents on my argument. So I'm going to do that first. So I'm going to have log base 2 of x minus 1 cubed plus log base 2 of 4 is equal to 5. Now at this point, there's 2 directions you can go in. So I'm going to go in one direction and then I'll come back to it and show you the other direction and see if you already had in mind what direction you would have went in. So one thing is to just kind of strictly follow what we've been doing and go ahead and add these 2 logarithms together. So if we add these 2 logarithms together, I'm going to multiply these 2 arguments. So my new argument is going to be 4 times x minus 1 cubed. That's my new argument, and it equals 5. And then I'm going to go ahead and rewrite it as an exponential. So my base is 2, my power is 5, and I set that equal to my new argument. And I'm not going to expand out x minus 1 to the 3rd power. I don't need to. So I can get rid of that 4 without doing that. So anything 3rd power or higher, try to find another algebra solution to isolate the x before you start actually multiplying all of that out. You might be doing more work than you need to. So 2 to the 5th power is 32. And now I mentioned getting rid of that 4, and I can do that because it's being multiplied by the x minus 1 cubed. So I can just divide it out from both sides. And then I want to get rid of that cube. And of course, I can get rid of an exponent by taking the equivalent root. So to get rid of that cube, I'm going to take the cube root of both sides. And the cube root of 8 is 2. And the cube root of a cube, those are inverse operations, so all I'm left with is the x minus 1. So adding 1 to both sides, I get my solution, x equal to 3, that I need to check. So we had one argument up here that contained x, and if I let that x be 3, 3 minus 1 would still be positive, so I do get to keep that solution. Okay, I mentioned about 2 different approaches to this problem. So let me just go back and talk about that second approach. Anytime that I have in an equation a log of a constant, the other option that I have is to actually evaluate what log base 2 of 4 is, instead of adding the logs together. So remember, to evaluate this, I don't need my change of base, although sometimes you might. I don't on this one, because remember what a log is asking for. It's asking, what do you raise the base to get the argument? So what do I raise 2 to get 4? And of course, that answer is 2. So this right here is equivalent to 2. So what I could have done back in the beginning of the problem was, instead of adding these logarithms together, I could have had my log base 2 of x minus 1 cubed, and then evaluated that log base 2 of 4, which we just said was 2, and then I would have a single logarithm without actually adding the logs together. So now what I would do is subtract that 2 from both sides, so that now when I write it as an exponential, my base, my power equals my argument. Notice that when I do the 2 cubed, I am picking up right here in the previous approach. So if you recognize that you can evaluate a log of a constant and figure out what that is and go that route, you'll get the same answer as if you said, well, I didn't pay attention to doing that and I went ahead and added the logs together. You're going to get the same result either way. Okay, last example. Now, on this problem here, when I look at this problem, you might be thinking that, similar to back here in number 7, where we moved that 3 in as a power, that's what you would do with this 5. And you can do that. However, I have another way I can deal with that coefficient on ln, and that is I can divide it out on both sides. Over here, I couldn't divide by 3 because you had other terms on that side of the equation. But in this one, you've got 5 times that log equals 9. So the easier route, for me anyway, would be to go ahead and get rid of that coefficient by just dividing it from both sides. And that's going to leave me the natural log of 5x equals 9/5. And now that it's a single log, I can rewrite it as an exponential. So my base, when I see an ln, is understood to be, sorry, it saw that as a circle, so it changed it to a prettier circle. My base is e, and it keeps wanting to do that, doesn't it? Let me get rid of that option. Okay, my base is e, my power is 9/5, and I set that equal to the argument. So I've got e to the 9/5 is equal to 5x. So now on my calculator, I'm going to have to figure out what e to the 9/5 is. And when I do that, I get 6.049647. I'll give myself quite a few decimal places and then round it to the hundredths after I do the division by 5. So after dividing by 5, I get x is equal to 1.21. And again, I still need to check my answer, but if I plug in 1.21 into the original argument, that would remain positive, so I do get to keep this solution. Now again, back at the beginning, if you brought that 5 in as an exponent and rewrote the problem as the natural log of 5x to the 5th is equal to 9, and then rewrote that as e to the 9th equals 5x to the 5th, you would have still gotten the same answer. You just would have had to figure out what e to the 9th was on your calculator and then take the 5th root of both sides. So it just depends on how you look at the problem and what strikes you as the right move to make. And the more problems you do, the more experience you get, the more you start recognizing the easier route to go. But just keep working at it, and if you see two ways to do it, then do it both ways and find out for yourself which way you think is easier. So that wraps up section 4.4 on the two different types of equations. If you have any questions on the video or any questions on homework, make sure you email me.